Good afternoon. Can you hear me there? Okay. Good afternoon. Today we will talk about distributed tracing. Let me introduce myself. Nice. Okay, sorry. I'm José Carlos Chávez. I work as a software engineer at Typeform. Typeform is a platform for creating conversational forms. Basically, your users or humans are able to create forms and then collect their answers, but they get the feel like respondents get the feeling that it's not a online form, but it's a conversation instead. That's why it has a high completion rate compared to others. I am also part of the Sipkin core team, which is an open source distributed tracing tool and a Datadog consultant in terms of distributed tracing. Before we start, I have a confession to make. From talking to people in the past, I realized that I tend to say he when I talk about a developer, when I truly mean he or she. As you can tell, I am not a native, so please know that if I say he at some point, it doesn't reflect my intention. I truly want to say he or she. So now let's talk about distributed systems. Yeah, distributed systems. Well, a distributed system is a collection of independent components that, from user perspective, act as a single coherent system, right? Distributed systems have three main characteristics. The first one is concurrency, which is about dealing with many things at the same time or at once. The second one is that there is no global clock. That means that components have their own notion about time. And the third one, and probably the most important for us in this talk, is the independent failures. There are three sources of failures, actually, in distributed systems. The first one is failures in the host. If we talk about a computer system, we could think about a failure in the computer hosting the service. There are also failures coming from the actual service or the actual component. Let's say there is a 100 exception bit thrown, or a fatal error, or a nil pointer error. Those are the kind of failures that occur at the component level. Or maybe a connectivity problem, but that's a different type. And then we have a third source of failures, which could be communication problems between components. Again, talking about computer systems, it could be related to network failures. There is a very nice quote from the book Building Microservices from Sam Newman, which says, network can fail and will fail. Can I ask you, to all of you, to take a couple of seconds to think about a distributed system? Maybe some distributed system that you are familiar with, or some distributed system that you are working with lately, right? Okay. As most of you and me are software developers, I will say that each of us have a different picture about how a distributed system looks like. Because of our circumstances, because of the kind of projects you work in, maybe the size of your company, or maybe the type of industry you are. So in order to make things simpler, let me introduce a distributed system that we are all familiar with, which is this. This is a very familiar distributed system for all of us. As you can see, it's a collection of independent components that, from human perspective, work as a single coherent system, right? So, in this very simple distributed system, we have a tap, and when you open the tap, the water flows out, right? Pretty simple. You don't know about internals, and that's all right. I don't either. So, let's say we have a small issue in one of the pipes that is causing a block in here, but it's on a small block, right? So the water will take a time to flow through the pipes, and eventually the human will perceive that there is a latency, We'll wait, but the water will come out anyways, right? Let's say now that we have a much bigger problem. Let's say that we have a massive block in one of the pipes, right? And the water doesn't flow through the pipes and not through the subsequent pipes. Then the user will perceive that the water is taking a bit to flow, and eventually that human will wait and wait and wait up to the point he or she will realize that water is not flowing. There are two interesting things here. The first one is that this guy is yelling in Unicode, which is good. The second one is that this person will perceive that there is something wrong. This person will perceive that there is an error somewhere. But he or she might not be able to point out where the error comes from. What is it causing? Why? Right? So, does this situation sound familiar to you? Can you think of a situation where you, from your perspective, you feel that there is something that is not working or there is something that is wrong, but you are not able to pinpoint where the problems come from, right? For me, it's almost a déjà vu. And it's almost a déjà vu because modern internet services are implemented as a complex, large-scale distributed system nowadays, right? When you had a system with a couple of components or a small system, you could easily pinpoint the problems just by looking at one single component in isolation. Now, a user request traverses dozens of services. And that means that before you solve the problem or you try to solve the problem, you have to understand how your components interact together, right? This is an API, as you can see. This guy is hitting an endpoint, trying to get information out of the endpoint. In this structure, we have an API proxy in front of all services that it's authenticating the request, saying, okay, this guy can access to this resource, or this guy cannot access to this resource due to a scope. And then once the authentication is done, then, okay, the API proxy is hitting the media API, and the media API is grabbing resources from the image service and from the video service. Right? Pretty simple. And let's say we have a small latency here in the image service. Right? That small latency will be propagated across the services, from the image service to the media API, and from the media API to the API proxy. And then in the end, the user or the client will perceive that there is a latency. And we said, all right. Depending on your use case, that's acceptable or not. But in any case, an engineer looking at this overall situation might know that there is a problem, right? Might see that, okay, one of the services is taking so long. Maybe the problem is while reading from the database. Maybe the problem is the connection between the components. But might not be able which service is at fault. And that's because with microservice architecture, you not only include a shift in the technical mindset, but also a shift in the cultural mindset, right? That means that teams now are more independent. And that means that me, as a developer, don't have to know every single piece of the internals of other team services, right? Because then the ownership concept is introduced. And even if I know what are the services included in one endpoint request, I am not an expert on every single service, right? So this doesn't give me, like the fact that I know what the services are included in that use case doesn't give me a hint on how to solve the problems. But let's go further. Let's say there is an error in the out service. And this error is causing that the out service cannot connect to the persistence. Let's say it's MySQL, and that service receives a TCP 2003, cannot connect to the server error. That error will be propagated to the API proxy as a 500 error, internal server error. And that will be propagated to the user as a 500 error. Again, how can you solve something if you don't understand how your components work together, right? But let's go back to the top where things were simpler. Because wouldn't it be so nice if you one day are on call duty and then there is a problem, there is an outage, and the error yells out and say, hey, I am here. I am in the first floor distribution. I am clogging the pipe. Right? That will be awesome, because then you will know what is happening, where, and how is it affecting the other components. Right? And you may be thinking, okay, we have that in computer systems, right? We have something called logs. Because, yeah, we do have logs. And logs are great. Problem with logs is that logs are focused on events. Logs are meant to represent events in the time. And if you look at this case with this distributed system, the usual case is not that you have one client requesting one endpoint, but you have something like this, right? Concurrency hits you back. And then, because services and machines might be shared simultaneously and might be requested by different clients, right? So these kind of situations will end up in this set of logs, which I keenly colored for you so you can identify which is corresponding to which service. In real life, that might or might not happen. Let's say you have Kibana and you can tag logs with services names. Because logs represent events in the system. There is no scope around logs. So, for example, can you tell me whether this sky blue record is being connected with one or either the first or either the second green one? Maybe not. Or maybe you can say, okay, I could include the request ID and I could correlate the logs. Yeah, but again, logs doesn't express how the causality is, right? Which one originated which one. So it only relies on a temporary relationship, which is simple to understand when you have just a few services, hard to understand when you have so many services. So logs will tell you that something happened, but not what happened and how is this affecting the other components. Then is when distributed tracing comes. Because distributed tracing will unclog your pipes. How? Well, distributed tracing, first let me explain what it is a way to understand what happened in your request. You can think of it as an action replay, or basically what happened in your request, right? You can look at it, you can look at the request and see, okay, this and this and this happened, and now I understand what is going on. A trace tells you the story of a transaction workflow as it propagates through your distributed system. From a request perspective, you can know what happened and when on each service, and you can know how your services are connected and how they work in the critical path. That's a very important concept that we will explore later. And finally, it's important to mention that distributed tracing is complementary to other observability means. Distributed tracing is not meant to replace logs or overcome logs, right? It's complementary. So last year, Peter Burgon came up with this diagram about observability means and how they are complementary, where they are, where they work together, and what are the boundaries around them. Logs tell you that an error has happened. It's focused on events. Metrics tells you that this type of error have happened this so many times. It helps you to identify trends. Whereas distributed tracing tells you what happened and the impact of that thing that happened propagated across your components, right? So distributed tracing is aimed to convert this and this into something like this, which is a request scope timeline shared, or shared timeline, which express causal relationships. As you can see, the API proxy creates two child operations, one in the auth service and the other in the media service. And at the same time, the media services create two operations, one in the image service and one in the video service. Its request scope is timeline. It expresses causal relationship. The concurrency is muted, basically, and also allows you to include more information with logs and tags. in some cases, you have a load balancer for each service, and then you want to see which instance of the service has been hit. Right? That sort of information can be added as well as tags. So let's explain the elements of distributed tracing. Well, the first one and the most important one is a trace, because a trace shows you an execution path, right? You can think of it as a trace being a full story of something, and then the spans that we will see later are each side of the story told by each actor, right? Then you have the context, which is something that you propagate across the components. It's like every time me, as a part of a request or as a part of a message flow, tell every single component, this is the request I belong to. So that information can be collected in one trace. The context can be propagated through HTTP headers, if we think about an RPC call, through Kafka messages, SQS messages, RabbitMQ messages. Now we have the spans, which represents atomic operations in systems, right? It could be a database call, MySQL query. It could be an expensive operation like a marshalling. It could be an HTTP request. It could be whatever you want to represent as a single operation. And then you have tags, which help you to group spans, for example, with a common characteristic. Let's say these spans are errored, these spans belong to this instance. In the specific case of Typhon, for example, what we do is that since everything is around forms, what we do is that we tag our spans with a form ID. And then we can see, okay, these are the problematic forms. Let me inspect all traces belonging to this form, right? And then you have logs, which mark meaningful moments in the span timeline. For example, in the previous graph, we have that at some point, the image service tried to retrieve the resources from the cache. And since the resources were not in cache, then retrieved from the persistence. This kind of annotation helps you to understand why this operation for this specific resource took like 1 millisecond, and for this other resource it took 10 milliseconds. Because there is a difference, because one could retrieve from the cache, one couldn't, right? Some vendors don't include the log API, some does. As I said, distributed tracing is meant to be complementary with other observability tools. So, like for example, AWS X-Ray connect the distributed traces with the logs, and then it provides the full stack of observability. How propagation works now? Well, as I explained it briefly, propagation is the mechanisms where you give the context from the trace to the other component you are talking to, right? So in this specific case, we have a request or a message produced somewhere. And then there is a connection to this Blueberry component, let's say, right? And then this component will retrieve the context from the propagation layer, from the HTTP header, from the metadata in a Kafka message. And we'll get, okay, I belong to this trace. Every operation that I do will belong to this trace. And we'll create spans for DB calls, for connection to an external service. And then once this component wants to hit another component inside the same system, we'll inject the context. Put in the headers, put in the metadata message, right? And the other component will do exactly the same, right? But what is included in a context? Like, what kind of information you add in a context? Well, the context information is supposed to be opaque, but for didactic purposes, we can inspect what is inside. You have basically a trace ID first. The trace ID is meant to group the full or identify the full trace. In most of the cases, you match one trace with one request. I am constantly talking about requests, but it could be another model. It could be producer-consumer. So yeah, it includes the trace ID. It also includes the span ID, because the RPC call that I receive is probably a span in an upper component, right? So I need to know that I am the child of that. And it also includes a sampling flag that I will explain later. So that's pretty much the information that is being included in a propagation. Okay, so let's now have a look at the benefits of distributed tracing. Because so far I have been explaining what it is and what solution it provides, but what are the real benefits to real problems, right? The first one is that it provides effective monitoring. Because first of all, it provides you immediate feedback. Like the collection of traces is almost real time in most of the cases. It's well scoped because you focus on one request. And more important, it provides actionable feedback. As soon as the trace tells you what the problem is and where it is, you can go and fix it or schedule a change in the process in order to overcome that problem, right? Another benefit, and probably one of the benefits that has more impact, is that it gives you a system insight. It helps you to understand how your components work together. And clarifies non-trivial interactions. You could have synchronous, asynchronous interactions, and this is distributed tracing perfect to identify, right? It gives visibility to the critical path, which is a very important piece in observability, because not every single part, not every single operation, not every single connection is part of the critical path, right? Back in 2006, when Google was moving to microservices, by that time it was not called microservices, but they were doing microservices. There were teams trying to improve the latency in their components. And some of the teams were spending loads of resources and time improving the response time in operations that were out of the critical path. Because without such a system insight, you cannot know by heart which improvement in latency will impact the most from the user-facing latency, right? I could improve different parts of the systems that are not part of a critical part, and then I will have zero impact, maybe, right? If you don't understand how they are working together, you won't be able to understand how to improve the latency. And another important piece, and last but not the least, is that distributed tracing, or in distributed tracing, the request effects are not constrained to request lifecycle. That means that you can have in a request a synchronous part, a asynchronous part, and they both are part of the same trace. That I will show you an example. So that helps you to understand what happened with your information once you went back to the client with a response. And you might be thinking, okay, this sounds good, but what about trade-offs, right? Because in software, everything is about trade-offs. What about the overhead? What is the overhead added by adding these fancy observability tools? Well, of course, there is an overhead, and that's why observability tools are designed to be unintrusive and are designed to include the minimum overhead possible. At least they are meant that. Google introduced this concept of sampling in their paper called Upper, where they decided to not to record every single interaction in their system. They just recorded a sample of it, right? Because for big systems like Google that has a lot of traffic, you don't need every single request to understand what is happening. And that's why Google introduced this as a measure of reducing the overhead. For high traffic systems like Google, you probably need 1% or even less of sampling. For small or not high traffic systems, you probably need more to understand what is happening. It's a matter of finding what is your way, right? There are different strategies to do sampling. It's also about to see what you trace and how much time do you retain that information. Another interesting point in overhead tells you that you might want to instrument only common frameworks. And that is not part of the overhead in terms of operation, but it's part of the overhead in terms of development. Because if you instrument common frameworks, then it will be very easy for other teams to get involved and get engaged with distributed tracing. If you provide implementations so they feel like they are using the actual library instead of using an instrumented library, then it will be easy to adopt, right? And finally, don't trace every single operation in your system. Only instrument the ones that you want to observe. For example, I don't want to observe that in my system, 1 + 1 gives me 2, right? That's a pretty trivial operation. What I probably want to observe is what happens if I am summing up long numbers, or what happens if I am doing tricky marshallings, right? These kind of things that you want to observe, I want to instrument. So now let me introduce Sipkin, which is an open source distributed tracing tool, as I said before. Right, Zipkin or OpenZipkin is a distributed tracing tool. It was created by Twitter at the very beginning. Before that, as I said, Google published a paper called Dapper in 2010. But it was written in 2006 where Google was trying to overcome the latency. So based on that Google Dapper paper, Twitter created Sipkin in 2012 as a mean to understand their latency and then have actions on it, right? In 2015, it became open source. It's a very mature tracing model. It has a great community. It has a lot of contributors, mostly users around the world. And yeah, I invite you to look at the Twitter or the Gitter if you need any help. The community is so kind and so helpful. Basically, Sipkin architecture is pretty simple. You have your service, which is instrumented, which is sending tracing data. There is a transport layer, and it could be HTTP, it could be Kafka messages, it could be gRPC. And then we have a collector, which is collecting all the information from the traces. And that is basically doing some translations and putting it in a storage, which could be Elasticsearch, it could be Cassandra, it could be MySQL, depending on your size, right? And then, of course, there is a UI hitting an API and showing you the traces, something like this. And here you can see that, well, you have traces, you have information about the time they took. You can filter by service if you want, right? You can filter by span name because, yeah, sometimes you want to see a specific spans that you know that are problematic. You can order from the longest to the shortest, from the newest to the oldest. And you can also show specific segments in time, let's say 1 hour, 2 hours, 6 hours, right? this is how a trace looks like. Basically, here what we have is that the API proxy started the operation, because it's the first point of contact, right? So the API proxy starts on a span, and then hits the authorization service, and by that there is an span as well here. You can see the head auth user ID. I don't know if you see it properly. I hope so. And after that, once it validated that everything is all right, the API proxy hits the media API, and the media API hits the image service and the video service, right? Everything is recorded here. So actually, you can see what is happening in your request. And as I said, you can add additional information like this. You can see what kind of request was it, what was the status code in the response. You can see what instance actually the request hit, and what was the request ID. Because as I said, distributed tracing is aimed to be complementary to logs, for example, or metrics. So yeah, you correlate the trace with logs through the request ID. And what happens if there is an error then? Okay, how can how an error trace look like? Well, it merely looks like this. As you can see here, first of all, you can understand how the error is being propagated across components, right? In the right side, in the bottom, you have that the auth service produced an error, and that error was propagated up to the media API. And sorry, the video service had an error, and that was propagated to the media API, and then the media API error was propagated up to the API proxy, right? So this is more or less how an error looked like. And what happened with asynchronous operations? Well, asynchronous operations are like this. As you can see, you have the synchronous part on top, and you have a big span on top, which is the synchronous part where the user makes a request and receives a response. But let's say you have a tracking service that occurs and starts right after you serve the response to the client. Well, it's part of the trace, right? So if it's part of the trace, you can still look at see it here. And that's why I mentioned it that request effects are not constrained to request lifecycle, right? Okay. And this is great, but how do I actually get the insight of the service that I promised you distributed tracing will give you? Well, Sipkin also provides a dependency graph, which is this. Well, in this dependency graph, you can understand that the API proxy is hitting the out service, and then it's hitting the media API, and the media API at the same time is hitting the image service and the video service, and then consequently it's hitting the tracking service, right? And this is a dependency graph for our use case. This looks simple, but believe me, you will really appreciate it when you have this dependency graph, right? That you cannot even see. So this is extremely useful in those cases, right? So yeah, this is distributed tracing, and I hope it took your interest. If you have any question, I am open to that. There is a look around section. This is an idea I got from a talk yesterday, where you can see some more resources to read and watch about distributed tracing. Thank you.
So we have time for questions from the audience. So do you have some question that we like to address? Okay. We have only one microphone, so.
Hi, thank you for your talk. Can you compare Zipkin to Stage Monitor?
Sorry?
Do you know Stage Monitor? Can you compare Zipkin to Stage Monitor, another tracing tool?
I don't know Stage Monitor, sorry.
Okay.
So sorry.
Okay, do we have other questions from the audience?
I just wanted to ask how hard or how is the steps to start implementing it? as you didn't mention it.
Okay. I will say that it depends. This distributed tracing thing is pretty new. So if you go to Java World, for example, it's quite famous. So you will find a lot of implementations for different frameworks. And actually, the community in Java is very strong. So you will find a lot of help and information around. If you think about Golang, things are just popping up. There are not so many frameworks instrumented. That's in one side in the research. If you really want to implement it in your code, I would say that it's not much of a problem if you find the right instrumented libraries. As I said, the idea of having instrumented common frameworks is that they actually feel like if you are working with the real ones, right, with the non-instrumented ones. So in that terms, it's not so complex. What maybe is the most complex part is to see what to trace, right? And that usually comes from SI error, right? One day you are on call and then you see that something fails and then you want to understand what is happening. And you say, okay, why I am not tracing this use case? Then you instrument that, right? But in terms of code, it's not that much overhead.
Okay.
Just to that question, I did this like a year ago, and I found it very complicated when you have like old source code, like Spring 128 or something, and want to do this. It's very difficult. You have to work around a little bit. So maybe for this, and then my other question, you said just monitor the stuff or trace the stuff that you're interested in. When you like use the Spring in Zipkin stuff, then you usually instrument the REST template. So how do you do that then to differentiate?
So if I understood correctly, when you instrument your application, then you have to instrument different parts. That's what you told me?
No, I mean when you like getting a request and you go on to the next one, and then you use the REST template. So you have to have two. If you one that's instrumented and another one that's not.
Okay.
Is there something built into Zipkin to say just this one and this one?
Yeah. I got it. So this concept of sampling that says that, okay, I trace this request, I don't trace this request. What it does underneath is not that it doesn't create traces for the non-sampled request, but it creates NOP implementation of the traces. So if you are creating a span for a request, if the sampling is false, the tracer will create a NOP span. And basically that NOP span has no information. It fulfills the interface, it has all the methods like real span, but it doesn't have anything. And once you report to let's say to the Sipkin server, the reporter will see, okay, this context has sampling flags equals false, I won't do anything. But anyways, the tracing objects are there, right?
Okay, so this one.
Hi. How do you integrate like passive components, like for example Varnish or other caches or something like that in this whole picture? Because it's different than you instrumenting your application, for instance.
Okay. So, for instance, at Typhon, what we have is that we have a proxy in front, right? And then that proxy is the one that decides, should I trace this or should I not trace this? And if you go, for instance, for Varnish, then the trace will end in the Varnish server, right? Varnish serves the request, and I will probably tag it as cache. And I won't observe that much there because that's a cache response, right? So it's just a matter of putting something in front, the first point of contact that I said, to resolve whether I am tracing this or I am not tracing this. If I am tracing this, I have started with this context.
Okay, we have.
Thanks for the great talk.
Thank you.
I have one question. You said in the beginning that one problem of distributed systems is that you don't have a universal clock. How do you overcome this? Like, how do you show what time was spent between services, so to say, like on the wire? How do you get to this?
Okay. So that's a very interesting question. Basically, when you have different services with different clocks, there are different strategies to overcome the desynchronization problem. When you start a trace, you start with a timestamp. And then when you finish the trace, because you responded back to your client, you finish that request, and you save the duration. So you have your timestamp and you have your duration. There are approaches. The first approach, of course, is to try to sync as much as possible your clocks. But for example, Pinterest, I guess, came with this approach where they receive the traces, and then every trace they receive, they try to normalize. For example, if you have this trace and this trace, which is the child, if this is like this, then they will take this difference and will try to adjust to put it here. But this is like modification after you receive the request. Otherwise, there is no way to like align your clocks. So yeah, this is an interesting approach that Pinterest did to overcome this no global clock problem.
Yeah, I have another question about the sampling. You said that you decided the point of first contact, if you want to sample or not. Mm-hmm. Is there a way to change that during the trace? Like, if an error happens, then I say, okay, now I want to trace everything?
That's another interesting question. So a colleague of mine asked me like 5 days ago, can I do like, if in a service there is an error, I say, okay, now I sample this? And the answer is no, because when you, like, since everything is distributed, if you propagate a sampling decision, then the upper components, as I said, will create nope spans, and that means that they won't carry any information. Because there is no way for them to know that after or later they will have interesting things to sample. What is true is that in not so big companies, it's very, like, when you don't have so much traffic, it's crucial that you save these error traces so you can understand what is happening. So there is one approach called firehose mode, where, and I guess Yelp presented this 2 months ago, in February. Basically, what they do is that they have agents that are receiving the traces, and then once one of the agents say, okay, this is a trace with an error, like sampling rate at that time is 100%, so they basically record everything in agents. Then the agent says, okay, this has an error, it's interesting, I will notify all the other agents to not to drop this trace. And that you can, then you can, right? But it requires infrastructure around it. It's not a trivial problem.
Okay, do we have another question in the very back? Okay.
Hi, thanks for your talk. That was great. I just have one question. Imagine that I have, 100 REST web services talking to each other, and at some point of time there is an error. And is it also possible, or I think that's also possible to track the responses, the requests and the responses between the microservices in this tool? How does it get along this tool with the contents of the requests and responses? For example, because if I have this kind of error case, I need to trace also the customer data, which are kind of sensitive, and how does it get along also with the new GDPR regulations? Because in this case, the tool would be data collector. So if the customer doesn't explicitly say, yes, I want to have my data saved in this kind of tracking tool, I am not allowed to save them in those tools anyway. Thanks.
Right. So yeah, GDPR basically came to all of us. So in common instrumentation for frameworks, sensitive information is usually not being tracked. For example, if I go to one of the slides here, you will see that basically track the HTTP URL, but I don't track query parameters, because they could include an API key or any sort of personal information or private information, right? So standard frameworks, they don't include more information than the HTTP response code. Maybe the body size at some point, the response size, but not specifics of the specific data. For example, in a SQL query, you might trace or tag with the SQL statement, but with the wildcards. You won't probably add the specific information of the user ID and what resources I am querying. So yeah, you basically don't log any sensitive information here. You shouldn't. Frameworks don't do that. And if you do your custom instrumentation for something, you shouldn't do that. You should try to anonymize as much as possible. And we had this problem 2 weeks ago because we were tracing at some point yacht as a tag in our authorization service. And yeah, we just removed that because it's GDPR, right? And plus, it's sensitive information. We shouldn't be storing that.
So if I actually... sorry. No. Wait. Yep.
Sorry. So if I'm just exchanging customer data all the time, and in every HTTP request response there is some kind of sensitive data, I'm not allowed with this tool to track literally anything. So if I have this bug scenario or error case, that doesn't help me much to reproduce the stuff, right?
Because no, well, you will trace the request. You won't add information. You will say, okay, I request this endpoint. If you see it here, well, it doesn't. You cannot see pretty well, but it says /media/user ID. You don't even trace what user ID it is. If it's very sensitive data. In our case, we store the form ID, but that's all right. So you can trace that there was a request that was hitting this and this service, and you don't have to add more information than that, because you will see, okay, for this, let's say you can store the user ID, you can say, okay, for this user ID, when I retrieve its profile, it's taking a lot of time, right? Okay, there is a problem here. I instrument the underlying connections. Okay, it's because it's retrieving photos, it's retrieving videos. You can trace those requests. You don't have to store more private information.
Okay, one question.
I have just more than just an add-on to your question. I just saw that you can log the trace ID. That there's possibilities to add the trace ID to your logs, and if you do that, then you could look into your logs and log something there. So that might help.
Yeah, logs also have the same concern with GDPR, right? You don't want to save sensitive information in logs. Yeah. You can get more information out of logs if you use the request ID, which is not sensitive at all.
Do we have one last question? So otherwise, I would like to say thanks a lot for your talk.
Thank you.